shooter part, but we will dig in. The third area of safety is active shooter. Now, what do we do in case of active shooter? Now, number one, I'm hard of hearing. So y'all are probably going to hear the pop pop first before I will, okay? If you do, and you are at all thinking it could be gunfire, or the rapid fire of a semi-automatic, automatic, or just individual shots, if you think it is, you stop me in my tracks and say, that sounds like active shooter. What should we do? Say again?
That's a good option, but we don't have it, man. He said shoot back. But we don't have our gun in here.
I have a feeling that I would be at greater risk being in the crossfire that way. So I'm kind of going to vote against that one a little bit. Okay? Number one, I believe every door coming into the building says no firearms, okay, or weapons. So hopefully no one will be shooting back. Okay? Now, what do we do? And what were you saying? Stay in the room. That's certainly something we'll do, but a little bit better than that. I have a key for this room. Okay? Now that's the good news. The bad news is
you can't lock these doors.
Not from inside. Okay? It doesn't have any buttons here. It doesn't have any buttons here, so I can't even press a button. I have to go outside, lock the door, and come back in before you close it on me. Okay.
Close it before you come.
Yeah, you were thinking that. Okay. So, I will close it and come back in. Now, as soon as y'all hear, and you'll probably hear it first, that somebody get on the horn, okay, and number one, if you've got it, let me get closer to my microphone and pick this up. The door I usually come in, I can't remember if I saw it this week, since I've been back, but it used to have the phone numbers for the campus police on it. One for Birmingham campus, one for Bessemer campus. If you can find that information, I would put it on speed dial in your phone. Just in case you ever needed it, you could just dial it immediately. Okay? Now, if you don't have that number, then 911 is next best. Best would be call our campus police. Because it could be they're touring around over on North Campus, and don't even hear it. So hopefully someone would, but in case they don't, you do that. So there's, do that. And as soon as you dial 911 or campus police, then turn your phones off. We don't want them ringing when he's walking by. Okay? So turn your phones off. Okay. I'll lock this door. But here's the next bit of bad news. There's another entrance to the room here. Okay? Now, I'm going to try not to disturb them any more than necessary, so I'm going to close this door. Okay. I'll close this one too for now. Here's the worst bit of bad news with it. Well, number one, and this is a bad news, but there's a class over there. They have no way, and I have no way of locking the room door coming in from the hallway into their office, into their classroom. So we're going to invite them to come over here. If they're having class and we hear this in this room while we're here, we're going to have them come in here too. Now, I can't lock that door. I don't have a key for that. But we can close that door. Now, this door does, fortunately, have a lock with buttons right here, so it's locked. But it's locked from the inside, not from the outside. So don't lock this door. He can get in, but we can't get out. Okay? So I have a key for that too, but that will take a place of time. Now, here's a door with a deadbolt, but I don't have a key for that. But then that door, we've already closed the door to the hallway, turned off that light. That door has, just like this one, only it locks from the outside, but we can get out from the inside. That's the door we lock by pressing the button here. So we close that door, get those people in here, turn off the light, lock that door, close this door. Why do we close this door? Because that door has a window. He can see in. Okay? We don't want him seeing in. We don't want him knowing anybody's in here. So we close this door, and then we close this door as well. So even if he gets in, he won't leave. Okay. So we've secured ourselves as much as we can. What do we do? Where do we go? With the folks next door now. All right, here's Terrell. Where do we go? The safest place is right over here. All of us get right over here. We're very quiet. We turned our phones off. We're not talking. We're not doing anything else. We're being very still. Now, why? He can fire through the glass. He can fire through the wood. He can certainly fire through this mesh down here. Okay? So we don't want to be anywhere where he can see in here or anything else. We're over here as quiet as we can be. Okay? We've done all we can to secure that. Now, it's true, if he knows we're in here, he can break the glass there, come in that door, and then there's nothing to keep him out. But as long as we're very quiet, that door's locked, this door's locked, all the rooms are dark, he has no reason to think anyone's in here. Now, if it did come to it that he did intrude into the room, even though there's not much hope of anything being here, if he did, you don't be the heroes. Okay? Your life is in front of you. Mine's mostly back here. Okay? So if anyone's going to do anything, let it be me. Okay? If I do get them down or something, I'll work them to kick the fire out of them, or whatever. But we hope it won't even come to that. We hope it won't even happen. As far as I know, there's only been one shooting on a community college in the U.S. And that was many years ago, somewhere in the Midwest or somewhere. It wasn't here, anywhere close to us.
Wasn't that the terrorist in Sacramento who shot the community college?
What's that again?
I think it was the terrorist in Sacramento was the one.
It may have been. Maybe it was far away.
That was like in 2015 or something like that.
Right, yeah. We happened to be, I was taking the class that meets on Thursdays, Tuesdays and Thursdays, is a physical science class. I usually take them to Channel 13 weather station for their weather and climate lab, because I can't do much here. And Jerry Tracy hosts us. And we happened to be there the day that it happened in the morning. We were there that afternoon. Here came a bunch of community college students into their studios, so they interviewed two of my students. So that was sort of a special time for them. And that was about the time.
I think it was also about that time when I was in high school, our physics teacher told us, if anything like that ever happened, we have the dial caliper. Excuse me, a dial caliper set so they could crack a skull real easy. So the plan was, because there was nowhere, and there was no corner there, no was invisible from the door, so we would just stand on either side of the door with the dial caliper.
Okay. All right. I did not mark that new kid, whoever he was who came in. I got Terrell here. All right, so we're only missing Daniel, I'm sorry. Then he may be in. He works and comes as soon as he can get off work. All right, so, yes.
I'm going to be in my physics.
Yeah, okay, that's fine. Yeah. I understand.
Yeah.
So, question is, any questions on active shooter? Okay, on any of the safety issues? Okay, good deal. All right, now, let me update you on what's happened since we last met. I don't know if I remember telling you all or not, but my wife had surgery on Thursday, and I wasn't on campus all day on Thursday. So we had to get up like 4 in the morning, and she had to be at the surgery center before 5. We were there before 5, and it was a while, but not too long. I'd say she was taken out of waiting room around 5:30, somewhere around there, plus or minus that. So from that time on, while she was taken back there, doing all the pre-op stuff, all the preparation stuff, and they go around and ask questions and stuff, that was all her. So I was by myself, so I was working on syllabi and everything I could. I think everything caught up, okay? So if you go to Blackboard right now, when you get to the home page for this class, on the right-hand column of Blackboard, you'll see a whole bunch of blue tabs. And they're in groups now. They didn't used to be, but there's groups. In the first group of blue tabs over here, about midway down that first group, about the third, fourth one over there, says course syllabus and book information. If you click on that, the updated syllabus is there. The one we went over in class, remember, was probably a year or so old. Okay, it's updated now. Everything's up to date on that. I think, not the blue. Okay, right below that tab, it says instructor information and something. If you click on that one, you'll see my locator card, where I am, blah, 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 phone number, office number, all that kind of stuff. And when I'm on campus, off campus, all that time. Okay? Then, whatever this means. Oh, I see. Okay. Then, after that, go to the next group, and in the next group, you'll see a tab about midway through it that says handouts, PPTs, and PowerPoints, and more. In that group, you'll find the research paper instruction. Updated, I got the correct months and things in there. Okay? You'll find no PowerPoints. The reason is this text has no PowerPoints to accompany it. So I'm going to be doing everything on the screen. Okay? So it's going to be messy and it doesn't go as fast. So sorry about that. This book provides absolutely no PowerPoint support. Okay? The research paper instruction is there. This is under handouts, PowerPoints, and more. So the research paper instructions is there. Been updated. I think I said that. Okay? And then the YouTube video link is there. And if you go to the YouTube video link and click on that, you'll see the top part are the presentations I made in class for the last class I taught. And then at the bottom, that's for the ones for this term. So right now, the syllabus one is there, which is everything we talked about on Wednesday. Question?
I was going to say, you still using the Cadbury books?
What's that?
Are we still using the Cadbury books?
No. This is a different book, okay? And I hope I mentioned this last time, but if I didn't, here it is. It's a first course in differential equations with modeling applications, 11th edition, and it's by a guy named Dennis Zill, Z-I-L-L. Okay, it is a Cengage learning book, so if you are on the Cengage Unlimited deal, you've got access to the book. Now, I think I have to get a WebAssign class set up for you to access it. If you can't access it without that, by all means. I had a student this morning who was looking at her ebook, and I don't know how she got there, but she was.
If you order like for me, I rented the textbook. Most of the providers will let you look at the e-textbook while it's in shipping.
I see. Yeah. Okay. So that may be it. Okay. But anyway, I'll get that done as soon as I can. Hopefully this afternoon, but it'll be hopefully sometime this week. Okay. It's sort of a pain in the neck, and I have to wait for Cengage to get all of this stuff. So I'll try to get it done as soon as possible. As soon as I get it, I'll put an announcement on Blackboard, and it'll go as an email to you, and it'll be on Blackboard from then on. So.
Is the book on the syllabus?
What's that? Yeah, the book's on the syllabus. Yeah, this is on there. So, yeah, if you look at the syllabus, you'll get all the information there. Now, so research paper instruction, the YouTube videos, and remember the old ones are at the top, the newer ones at the bottom. And as soon as we cover something on this term that I've already covered previous, I take off the old. So you should have, there may be a little bit of overlap, there may be some slight gaps, but overall it should be a fairly continuous thing. We don't cover the same amount of material every term, okay? If I last taught this in the summer the classes were an hour 50 minutes each, but only 20 classes. Now we have an hour and 15 minutes each for 32 classes. So yeah, so the classes will be different. All right, now, then also I put out there some websites that either I found or other students have found and said they found useful for the course. So I put those out there on under handouts, PPTs, and more. So that's all under that. Okay. Any questions on how we're set up? So everything in Blackboard should be ready to go. And here's what we have to use. Since there aren't any PowerPoints, I use this thing. It's just a blank PowerPoint. And I'll write down what I think you need to know. Now, right now, none of you have books. Is that right? So let's start in chapter 1. What's that?
Let me see if I can bring up my ebook still.
Yeah. Okay. Chapter 1 is Introduction to Differential Equations, which is a very good thing because that's what we're doing. Okay, first course in differential equations with modeling applications. Now, we're not doing very much of the modeling stuff. That wasn't in our course description, so we don't have to do that. So those parts I will sort of minimize. But let's start with the word differential equations. What do you think of when you see the term differential? Say again?
Minus, subtracting.
Okay, so basically you're focusing on the difference part of it. Okay, and certainly difference is there, the term differential, okay, but it was there in the terms of what?
It's the difference of a variable normally, like in an equation.
Okay, and that was what we used in
Algebra and calculus.
after algebra. We did it in algebra. We did it when we did slope, difference in y over difference in x. And what did that become in calculus?
Integrals and derivatives.
Derivatives. A derivative is a difference quotient. We called that difference quotient in pre-calculus algebra. We called it a derivative in calculus. What we called a differential in calculus, remember, a derivative could have been something like this. dy dx is equal to 3x. Okay? Now, if we wrote that as a differential, that became dy is equal to 3x dx. Now, both of those are differential equations, whether you write it in derivative form or in differential form. Why they just call it differential equation, I don't know, but differential derivative almost are the same thing, okay?
But isn't a derivative just a first order differential equation?
What's that?
Isn't a derivative just a first order differential equations, or do the higher order ones?
Yeah, okay.
Are they more
We'll be talking about those too, but yeah, you're right on the subject.
I think that's the key difference. We can go higher orders than
Yeah.
just this one.
But you can have higher order derivatives too. d2x dx squared, right? And so both of those are coming into play here. Now, an equation means it's equal to something. So a differential, by definition, is already an equation. And that is a differential equation, but what we were doing then would be to integrate that. Well, that's solving a differential equation. That is a pretty easy thing to integrate. Just put an integral on both sides, and you got it. Okay? I just this is a very simple one. If you integrated both sides of this, that would be y, the antiderivative of dy is y, is equal to 3, what? And here's, I can't remember, you go by Daniel or Dan? Dan. Okay, I was thinking you did, and for some reason I had circled Daniel on the roll sheet. So let me correct that, this Dan. Okay.
It's just one letter, Greg.
Yeah, okay. We, again, have had close to perfect attendance today. Doesn't look like it, but Terrell has been in and left, and so has Jordan. Jordan had to go to work, and you just got here from work, and Terrell is covering both physics and differential equations today. So anyway, so what's the antiderivative of x dx? X squared over 2, okay? And then, because these were indefinite integrals, we always would do a plus c. So there we solved the differential equation. I would probably have written that y is equal to 3 halves x squared plus c, but there's lots of ways you can write it. Okay. that is a simple differential equation. Differential means derivative or differential form written as an equation. That's basically all we're talking about. Now, some kind of equation that contains derivatives, whether this could be written as y prime. If you had second order, which, goodness gracious, I know your name and I can't remember it. I want to say, I was going to say Peyton. I had a Peyton in my last class who was P-E-Y-T-O-N. I thought I was getting that crossed up. You could have y double prime or y triple prime. If that's in an equation, that's a differential equation. Okay? And you can have a mixture of them. Okay? For instance, y double prime plus 2y prime plus y equals 0. That's a differential equation, okay? Because it does have an equation in it, and these have derivatives in it. Now, we also have the y there that you might say if the 0th derivative of y. In other words, it's just the function. And then the function's first derivative and the function's second derivative. So that also is a differential equation. Okay. Now, the first section here, that was all preliminary talk. The first section here is talking about definitions and terminology. Okay? And I'm going to write down, and by the way, Dan, I told the others, this book has 0 PowerPoints with it. So I have to write everything out on the screen. So it's not going to be a pretty picture at all. Okay? Here is a differential equation. dy dx, a derivative form, is equal to 0.2 xy. Now that's a little bit different kind of a looking deal here. What's that? Just they picked one, okay? And we'll, and I think just to be a little confusing to begin with, why this book tends to start with examples that are pretty far-fetched, and then you get to the general things. And I don't know why they do things that way. To me, it is a little backwards, okay? And some of the things they say, some of their verbiage, almost circular in the way you, sometimes it doesn't clarify anything for me. It just makes it a little more mucky. It may clarify it for you, I don't know. Here's their first sentence here. Since some of you do have books. Yeah, this is on page 3, definition terminology 1.1. Okay? You're the only one, I think, with a book right now. Oh, you got it? Yeah. Okay. All right. And this is absolutely true. It says derivative dy dx, okay, of a function, and they name the function y is equal to phi of x. Now, in my mind, why introduce another name? Just have y of x. But no, they're going to say y is phi of x. Perfectly fine. There's no reason not to. But I see nothing that makes it clearer to make a new name here. But it is indeed perfectly okay. And dy dx then would be, you could write this as y prime is equal to phi prime of x, which is another function of x, of course.
I don't know why they didn't use the pretty standard function symbol.
Or f of x, exactly. I do not know why, okay? But again, they have their ways. I don't know what they are. Now, and they do this, and to me this is not particularly helpful, but it does let you say. They give you an example here. Here's a function. Y is equal to e to the 0.1 x squared. Okay? And then, so here they write it as a function but they don't use the symbol phi at all, why not just leave it y of x? That would be perfectly fine, but that's okay. And then they say, this function happens to solve that differential equation, the one right above it. Well, let's see if it does. Okay, let's do dy dx, and what would that be? E to the 0.1 x squared, yeah. Whenever you type a function that's e in it, its derivative has that same e in it. But then you do a chain rule, and what else would it have? Times x, 0.2x, right? Okay. Well, guess what? Isn't that the same as 0.2x times y? So sure enough, that is a function that solves that differential equation. Because when you do dy dx, you get the same function out of it. Okay? So sure enough, that is one. Okay? And why in the world do they lead off with stuff like that? They give you a function, say, hey, look, this works. Okay? Well, if they always gave you a function, you wouldn't need to do differential equations, would you? To me, it's all about solving the differential equation. You coming up with that on your own. But it's going to be several sections before they get around to having you do that. So, sorry about that. This is what they're going to have you do at first, checking to verify that a given function does solve a given differential equation. Okay. What's that? Skip the first chapter? Oh, yeah, well, yeah, that kind of stuff will be, which makes for very tough questions, because basically, verify this is true, was you already know it has to be true, so you have to basically show me all the steps to let me know you know it's true, you know, because the answer you already know, because it already said verify that it's true, the implication is true. What's that? I don't think you want to, but no, okay. Yeah. So here is a definition. The equation we made up in 1, which was this equation right here, okay, is called a differential equation. So then they state it again. So let me give their definition. An equation containing derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables is said to be a differential equation. So let me write that out so you got it all. An equation, and I'm going to abbreviate like crazy, an equation containing, okay, the derivatives. Okay, that's derivatives. Yuck. It does this all the time. Okay. Of one or more, okay, unknown functions, okay, or dependent variables. See, y was the dependent variable, phi was the unknown function. That's a bad abbreviation, variables, okay? With respect to, the derivative is with respect to, RWT is with respect to, okay? One or more independent variables, okay, that's variables again, is said to be a differential equation. And when I'm going to say differential equation, right now I'm going to do DFF-EQ. In the future, it's going to be DE. Differential equation, DE. Okay? Now, To talk about differential equations, we're going to classify them according to three different ways. Okay? So let me go to a clean page here to start this off. The classification by type, by what Peyton was talking about earlier, order, or by linearity. My writing stinks. Linearity. It still stinks. Okay. Let me clean that up a little bit. I hate having to write all this stuff out. Okay. I miss my PowerPoints. I don't like. Okay. Linearity. Type, order, and linearity. Okay. Now, there's two types of differential equations. Okay? Only two. Ordinary differential equations and partial differential equations. This stands for ordinary. This stands for partial. Okay? Now, y'all remember what partial derivatives are? Okay, that little funny looking D symbol. When you have more than one independent variables, you take the partial with each one separately. Okay, that's the partial differential equation. Ordinary differential equation, we're strictly dealing with d by dx, d by dy, d by dt, something like that. You can have higher orders, but only one independent variable. Okay, so almost the entire course is going to be ordinary differential equations. We may at some point touch on some partials, but they're going to be very special case partial. This is not a course in partial differential equation. It's ordinary for the most part. Okay? Now, we're going to look at some in example 1, and let's determine what type they are. Okay? Okay, what type is that? dy dx plus 5y is equal to e to the x. What type of differential equation is that? Second? No, not partial. Partial has those silly looking d's. That is ordinary because those are d's. Not the partial is something that looks like that. Remember? It's that crooked little.
I always use the delta symbol.
Yeah, okay. This is a regular d. dy dx, ordinary. Second?
Delta is a really good way of denoting the partial.
I still couldn't hear my ears.
Delta is a good way of denoting the partial differential equations. I did see a professor do that once.
Okay, is this what you're calling a delta?
No, the triangle delta.
Okay. Yeah, to me that doesn't say it. This is what says partial. dy partial of x, y with respect to
It's
x.
hard to make it out though.
Yeah, when I'm writing fast, in fact, the one on the bottom, you'd be hard pressed to say, what is that? Okay, but those are d's, not partials. And even in partials, sometimes we call them d's, but they are partial derivatives. Okay, how about this one? What's that?
That was like a higher order.
It's higher order, but it's still, the type is ordinary. Okay? How about this one? What's that one? Those are ordinary because these are d's, not partials. D's. Now, what's different about this one, and all ordinary differential equations only have one independent variable. X in those two, T's in this one. That one had only y's for dependent variables. This one has x and y for dependent variables. X and y over there for dependent variables. But t is the only independent variable. And that's what makes it ordinary. Only one independent variable. Okay? And those are d's, not partials. Okay. Now, see if I can write them over here. No. Okay, what's that? Obviously. Partial differential equation. No longer D's, but those little crooked, ugly little things. Occasionally I've heard those called del's rather than D's, but a del has a different meaning too. That's your upside down delta, which you use for gradients. That is a del. So I don't know why some people call this del. But now you'll notice two independent variables, only one dependent variable, u, but it is dependent on two different independent variables. So that's why that's partial, okay? Because of the squirrely looking little d's there, okay? And by the way, that is I believe that's Laplace's equation. Not that you need to know it, we're not going to do this, but if in upper level courses you ever run into it, I believe that's Laplace's equation. Not absolutely certain, it's been a long time. Okay, here's one.
It's almost terrifying to be in DE and hear entire level.
Yeah, exactly. I messed that up. Messed it up grand way here. I thought this wasn't making a lot of sense. Okay. All right. What's that? Obviously, a partial differential equation because you have those funny looking d's there, and you have two independent variables, x's and t's. Now, I can't say this absolutely for sure. Excuse me, I got to sneeze. Sorry. But that is some type of equation of continuity. You don't need to know that, but because you have, these are usually spatial variables here, and that's time derivative there. Usually the t is time. And so this is an equation of spatial and time dependence. And usually that leads to what we call an equation of continuity, but you don't need to know that, okay? And then this is a fairly simple looking one. Okay? And that, of course, is, oops, I got ahead of myself again. Okay? That would be a partial differential equation. The reason because of the funny looking d's there. But this one's a little different from the above. These had one dependent variable, but two could have more independent variables. This has two dependent variables and two different independent variables. Okay? So anytime you have more than one independent variable, you all have to be dealing with partials. Okay? So that is those are partial differential equations. Now, they do say at the bottom, except for this introductory section, only ordinary differential equations are considered in this text. Except for this section here, where we're just introducing the nomenclature to you. So the type we're going to be messing with is strictly ordinary. But right now we're going to at least throw out some partials. Now, later in the course though, we will hit some things that you will take partial derivatives of things, but they're still going to be ordinary differential equations. There's a test that you do for exact differential equations, but you don't know what we're talking about there yet, and you take partials. Okay, that's the test you do, but it keeps the differential equations to be ordinary. All right, now, throughout this text, ordinary differential equation would be written using either the Leibniz notation or the prime notation. This is Leibniz notation, d by d, okay? That's Leibniz notation. That same one written in prime notation would be y prime plus 5y is equal to e to the x, okay? Now, the advantage of Leibniz notation is you know by looking at it what the independent variable is, okay? And of course, what the dependent ones are too, but that's also clear there. Looking at that, if you hadn't had an e to the x, if you had a 0 there, or 7, or minus 3/5 pi, or something like that, you still wouldn't know what the independent variable was. Okay, it could be t, it could be, you know, whatever. But there with the x being there, then you know it has to be an x. Okay, so, but the advantage of the prime notation is a lot easier to write. Okay, much more concise and clearer, perhaps, than that way. Okay, so we will use both of them, though. Okay. An earlier one, this one right here, would be, what would that be in prime notation? This one right here. Y double prime minus y prime plus 6y equals 0. Perfect. Okay? Now, you could do this one in prime notation, but it might be, this is one of the things that would have that disadvantage to it. You could say this is x prime plus y prime equal to x plus y, but guess what you don't know, just reading it that way. What is your independent variable? Is it z? Is it t? Is it theta? I mean, you have no clue on that, okay? So therefore, this is probably the preferred way to do it because you see all the players in it. This one is a lot neater looking, but you don't know what the independent variable is referenced to. Okay. But frankly, the independent variable is often just a dummy variable anyway, so it doesn't matter what you put it as long as you don't use x or y. Okay. All right. All right, and I think we've already, okay, just a few notes about the prime notation. Sorry, I've run out of room, so this is going, it's a little disjointed here. Sorry about this. Y is the function. Y prime is the first derivative of that function. Y double prime is the second derivative of the function. Y triple prime is the third derivative of the function. What goes next? Okay, no, they usually don't do many more primes than 3. Okay, after that, they start putting, and let me make sure I'm in agreement with the book. Okay, they put parentheses 4. Okay, that would be the fourth derivative of y. Okay, because you get too many tick marks up there and you either lose count or they smear together or you can't tell and that gets confusing. Usually a single, double, triple are easy to see. Anything past that, then 4 in parentheses. Why the parentheses? Because otherwise it would be y to the fourth power. No, that's not what we mean. In parentheses means fourth derivative. Okay, so anytime you see that. Now, at some point in my past, I could almost swear that they use Roman numerals for the derivative. Obviously, they don't use that anymore, so don't even go there. But that is what we mean by a fourth derivative. Okay.
The book is stopping on double prime. They're not going to triple prime.
What's that?
The book is just stopping at the double prime. They're not going to triple.
Well, are you on page 4 in the book?
Yes.
Okay, under notation.
I'm on page 5.
What's that?
I'm on page 5.
Page 5. Go back to page 4. Under the title notation. Do you see that right at the top of the page?
Yes.
Okay, the third line underneath notation. There's a y triple prime. Yeah. Okay. Now, in Leibniz notation, you don't have that to worry about because this would be dy dx or dt or whatever your independent variable was. This would be, this would be y as a function of x. This would be dy dx. This would be d2y dx squared. This would be d3y dx or dt cubed. This would be d fourth y dx to the fourth power. So in Leibniz notation, there's no need for parentheses or anything. You use numbers for them all. You don't use the primes. Okay? So we're not going to do that many with that high of powers. We could, but we won't have very many of those. Okay. Now, have any of you run into Newton's dot notation? Okay, you have. Yeah, Newton's dot notation, if it was dy dt, he would say y dot. And d2y dt squared, this is velocity, that's acceleration, that would be y double dot. Okay? Yeah, it's very similar. The thing is, primes are usually easier to see than dots, and dots you might have a speck on the page and you think it's a dot and it really isn't, you know. So we usually don't do that much. But when Newton was developing it, he used the dot notation. Don't worry about it, we're not going to use it. But if you ever run into it, then it's fine. Now, on the partial derivatives, you know how those are denoted, right? A partial of y with respect to x, what would be another way to say that? It don't use a prime. It uses y sub x, right? Or y sub t. That is partial of y with respect to x. That's a partial notation, okay? The subscript is a partial notation. And the subscript is the independent variable. The one on the regular line would be the dependent variable. Okay. So, I've already erased it. Remember the one that I had, second partial of u with respect to x squared, I believe it was. Is equal to second partial of u with respect to t squared minus 2 partial of u with respect to t. I said it's sort of like a continuity equation or something. How would you write that in subscript notation? U sub xx is equal to, no, you do x for each one, okay? U sub tt, oh, go outside, okay, never mind. Minus 2 u sub t, perfect, okay. Okay, so that's your subscript notation. though we're not going to do those except for this section, but just so you'll see it and be aware of it. Okay, so those are the types. And the only two types we deal with is ordinary and partial, except for this section and maybe a little bit in the homework and stuff. We're going to deal strictly in all the other chapters in ordinary differential equations. Though we may take partials of certain things, that's coming up, that's okay, but we're only going to be dealing with ordinary differential equations. Now, I hope it's not confusing to you, but sometimes we get crossed up. After ordinary or partial, which are types of differential equation, the next thing we look at is order of differential equation. And ordinary is not order, okay? So they sound alike, they're not the same, okay? The order of a differential equation, okay? And just things that I've written on the board so far, this would be a zeroth order because it's not even a differential equation. If that was equal to something. This would represent first order, second order, third order. In other words, what is the level of your derivative? Fourth order, first order, second order. Ooh, y'all let me get away with something. That's the D2U. Okay. Happy D2U. Okay. This is the second order differential equation because the maximum derivative is the second. But this is the second order partial differential equation. Okay. We start stringing the names together. Okay. So that's what order is. What is the level of the derivative? Now. And then for an example, they pick one that's really wacko to lead off with, which I guess is okay too. But here's one. Uh-oh. Okay. What would you say about that one? Okay. Okay. That's a power, it's not an order. Yes. That's a second order ordinary differential equation because those are all D's, so that's ordinary. The highest derivative is the second. That dy dx in parentheses cubed, that's the first derivative cubed. The cubing doesn't change the order, of the derivative. Okay? So we might say x cubed is a polynomial of order 3, but that's not what we're talking about. When we're talking about order in a differential equation, it's the derivative. And that's just a first order. The second term is a first order derivative, dy dx. It's just cubed raised to the third power. Powers and order are not the same. Of course, the 4y is not a derivative at all. And each of the x is immaterial. It's just, it comes into play, but it has nothing to do with the order of the differential equation. That's a second order differential equation. Okay. Now, and I mentioned before that you had things such as derivatives and differentials. And here is a very common way to write a certain type of differential equation. M as a function of x and y, okay, dx plus n as a function of x and y dy is equal to 0. Okay. Now we'll name that, in other words, okay. But, that doesn't look like anything we've done before. This is written in differential form. But because these are both d and d, no d squared, nothing else, this is a first order. Now, the part that's sort of confusing, it looks like there's two independent variables. So you would think these need to be partials. No, this is just a function of two variables, but the derivatives are dx and dy. You could write that if you subtracted this from both sides, then a pure mathematician would cringe to say this, divide by your dx. That would be then n as a function of x and y, dy dx is equal to minus m as a function of x and y. Okay? The derivative is only dy dx. Okay? No second order. That's the first order. Ordinary differential equation because those are d's and not partials. Okay? Strange but true. Okay. Here comes example 2. Okay. And again, let me clear the screen for this one. Okay. If we assume that y is the dependent variable in the first order ODE, that's not a poem I'm going to do here, that's ordinary differential equation, then recall from calculus that the differential dy is, and this is what we did at the beginning, if you had dy dx is equal to, oh no, this is a bit squirrely. Okay. Now that's just a statement that Leibniz notation is the same as prime notation. Okay. But once you have that, you could then do dy is equal to y prime dx. Okay. It seems like that's just being redundant, but now that is in differential form for whatever your function is. Remember, y prime is just a function of x, because x is the independent variable. So therefore, this is just a statement that dy is equal to some function of x times dx. That's differential form. And I'm not really sure why they threw this in at this point. Okay? But again, I'm saying it seems like to me that pure mathematicians would just go crazy on saying you multiply by dx or you divide by dx. But that's exactly what it looks like you're doing. And it is, in a sense, what you're doing. But dy dx is just an operator. And you don't multiply or divide by pieces of an operator. But it is doing the same thing. So I don't know. So here's a differential equation. This is what example 2 is dealing with then. So I'm going to clear again. Okay? Y minus x dx plus 4x dy is equal to 0. Now this is one like the one before we said m of xy dx plus n of xy dy is equal to 0. This is one just like that. This would be our m, which is a function both of x and y. This is our n, which could have been x and y. It just happens to have only x's in it. But that is a ordinary, because those are d's. First order, because those are only ones there. First order differential equation. Even though this looks like there's two variables here, there are. But this is dependent, that's independent, just because of the usual way we talk about them, that y is a function of x. Y is the vertical axis, x is horizontal axis. We usually think of them in that way. Okay. Now, can we write that as a differential equation in terms of derivatives rather than differentials? What would you do? Yes, divide both sides by dx. And I just chose to write it under only one piece of that. I could write it under the whole thing. But this then is what? 1. So now we have y minus x plus 4x dy dx is equal to 0. And if you wanted to write it in another way, you could write it as, there's several ways you could write it, 4x dy dx plus y is equal to x. There's another way to write it. Now later we will prefer this method, okay? Because this is sort of a standard type method. In other words, get all the y's and y dependents over here and anything without the y in it over there. Okay? So later on we will see this as a standard form. Right now we have no way of knowing that with all that we've had so far. But this is a first order, first derivatives here, first order ordinary differential equation. Okay? It didn't look like it necessarily. Well, yeah, we sort of knew it was that there. But this transformed it so it's obvious that is. In fact, in prime notation, that would be 4x y prime plus y equal x. Okay? Ordinary first order differential equation. Okay. Now, let's go the other way. Let's say we were given this. 6xy dy dx plus x squared plus y squared is equal to 0. Okay. And that is a dx in the bottom, even though that looks like it might be something else. Okay. Now, how do we write that in differential form as opposed to derivative form? Or multiply by dx. Okay? Multiply each term by dx. Okay? So here the dx's go out, and you have 6xy dy plus x squared plus y squared, and good idea to put that in parentheses, dx is equal to 0, because 0 dx is just 0. Okay? Now this is one that, remember our earlier, m of xy dy plus n of xy dx is equal to 0. And that's what you got going there. Even though you have two variables there, x is still the independent variable because it was in the denominator before, and y is the dependent variable. Okay? So they just interact in these other ways. Okay? So that is another form. Both of those are ordinary first order differential equations. Okay? Make sense? And you can move back and forth between them fairly easily. Now, there is yet another way, and they do this, and this can get, in my mind, a little confusing. But here's another notation you can use, and they do use it. Not right away, but we will be using it later in the term. Okay? Some capital F, which has nothing to do, well, that's not quite true, with y as a function of x. Let me put it that way. This is a capital F rather than a little f, okay? F of x, y, y prime, y double prime, they do a dot, 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 up to and including y to the n minus 1, y n minus 1, okay, well, we get there, is equal to 0. Okay. Now, f is what they call a real valued, meaning you only put real numbers in there, function of n plus 2 variables. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, up to n minus 1. But this is, let's count over here. 1, 2, 3, 4, 5, up to n minus 1. This will make it n, and that would make it n plus 1. So this is n plus 1 independent variables. Okay? You would think with that only having n minus 1 derivative, it would be n minus 1 or n, but no, it's n plus 1 variables. Okay. That's why, because the x is also a variable. Okay. Now, wait a minute. I'm sorry, I skipped something I shouldn't have skipped. Let me back off. Okay. I'm sorry, I got two things crossed up here. I was beginning to wonder why things were looking so straight. Okay. Another parentheses there, and that's equals 0. Okay. That's with an n there. Okay. Now, how many, that now has n plus 2 variables. That's what I thought it said, n plus 2, but we only have it. So again, 1, 2, 3, 4, 5, up to n derivatives, plus 1, plus 2. So n plus 2 independent variables. This is a function of those. Okay. Now, as a differential equation, that's only an nth order differential equation because that's the maximum derivative you have. So if you wrote that in terms of the other things, okay, and this is obviously by dx, x is your independent variable, this would be dny dx to the nth is equal to some other function, and here they use the little f here, and this would be of x, y, y prime. See, this is what I was crossing up, y double prime, yuck, dot, 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 y to the n minus 1. Okay, that's what I was trying to write, okay, before my eyes got on the wrong line. So this and this are basically equivalent expressions, okay? Because there's your f derivative term, so you could write that as some, and this and those else have nothing except the names. Because this is a capital F, this is a little f. But this is a function of all but that one. In other words, you separate out this one for itself, and then the function you have left over is a function of all the others, but not including that n, because that's over here. Now, if that looks a little confusing, it is, okay? Don't feel like the Lone Ranger. And they do some things with it, but when we're really using the functions, usually it'll make a little more sense than just everything being abstract right now, okay? How are we doing? Did we just run out of time?
3:46.
Yeah, sorry about that. No extra charge for the extra minute, though. Okay. All right. So we will pick up next time with, let me make sure where we are. Okay. We got a little bit more before we get to example 3, but then we'll go with that. Let me give you some homework exercises to do. This is a long first section here. But you can do some of the odds, 1 through 7. The reason I give you this is that the odd number, answers to selected odd number problems begin in the back at ANS 1. Answer 1, like an appendix back there. Okay? So do some of the odds 1 through 7. Do number 9. I think it's back there too. I think we stop there. We'll be picking up enough to do the rest of it later. Wait, no. Don't even do 9. Sorry. Just 1 through 7. State the order of the ordinary differential equation and determine whether it's linear. Okay. We don't even have the linear and nonlinear yet. So you don't have to do any if you don't want to. You can do the order part. Don't worry about the linear and nonlinear. We haven't quite gotten there yet. We've done order, type, and order. We haven't done the linearity yet. So hang on, we'll get there. Okay. Good deal. I don't particularly care for the way this book organizes things, but frankly, I have been through several different texts, and most of them are way beyond what you need in a sophomore level course, okay? And I finally talked with someone that taught at Jeff State, and she was talking about different. I said, what book do you use? She said Zill. I went and found it, and it comes the closest. I don't even remember the name of it. I had a text when I was in college for ordinary differential thing. It taught itself. I mean, it was just because I had probably the worst math professor on campus. And all I did every night, I went through, read the book. It was readable. It gave the examples. It all made sense. Of course, I had a great professor for calculus who had gotten us ready for it. So I was primed for it, and I could read the book and go, I wish I had that book. I wish it was still in print, but I don't even know who the author was. That was so long ago. I'm sure it's not in print, but it was a perfect book. He gets up in the clouds and sort of stays there, and then all of a sudden will come down and do something practical, and then gets back up in the clouds again. So I'll try to make as much sense as I can out of it. Take care. We'll see you Wednesday.